Welcome to the Walton Pi. This is going to be a test review for a calculus test that will cover derivatives, the product rule, the quotient rule, and the chain rule. If you are following my Calculus is a Piece of Pi series, this test review covers sections 2.1 through 3.10, so check those videos out if you haven't already, as it'll go in more in depth than this test review will. But without further ado, let's get into a test review for calculus. Are there any topics that people would like to go over? Feel free to just say it aloud, or you can type it in the chat. I can see that as well. Any topics that anyone wants to be sure that we go over?
Probably just like doing derivatives of trig.
Okay. Yeah, we can do trig derivatives. All right, so just in general, or with the limit definition?
We can do both.
Yeah, we can do both. Okay. So let's start with those. So let's see. So if we were to try and figure out what the derivative of sine of x is, for example, if we're trying to figure out what that derivative is, the limit definition is going to be the limit as h goes to 0 of sine of x plus h minus sine of x divided by h. In order to do this one, you have to be able to use the sine addition formula. So that is sine of a plus b is equal to sine a cosine b plus sine b cosine a. That's going to be what this one is. So we can rewrite this as the limit as h goes to 0 of sine x cosine h plus sine h cosine x minus sine x all over h. And then we have a couple terms that both have a sine x in them. So both this term and this term have a sine x. So let's clump those together. So it's the limit as h goes to 0 of sine x times, we have a cosine h minus 1, and we have a plus sine h cosine x all over h. And the nice thing about this is at this point we can break this up into two fractions. So we have both of them over h. And then this limit we can actually break up into the limit of the first plus the limit of the second. So sine x times cosine h minus 1 over h plus the limit as h goes to 0 of sine h cosine x all over h. Now, these are going to be where we have two trig limits that are very important to remember. Anytime you have to do the derivative of a trig function using the limit definition, your hope is that you end up with either this fraction or this fraction. Because those two limits are two identities that are listed in your textbook that are the way that we can approach these. So this limit, cosine h minus 1 over h, that is going to go to 0, and then sine h over h goes to 1. So what these turn into is we get sine x times 0 plus 1 times cosine x. So that means that the derivative is equal to just cosine of x. So that's what the derivative of sine x is going to be. The derivative of sine of x is just going to be cosine of x. What we could do is we could have gone through the same process to be able to get the cosine derivative. For that one, we would have had to use the cosine addition formula. And so that one says that if you have cosine of a plus b, this is equal to cosine a cosine b minus sine a sine b. And so if you were trying to do the derivative of cosine of x, you would have this, this property would come up and you'd get the same sort of thing. You'd have one piece go to 0, one piece would go to 1, and that's how you would be able to approach that problem. So if we were to just summarize the different trig functions, the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. If you can remember just those two, you can be able to figure out all of the other trig functions if you need them. So for example, if we were to try and figure out what's the derivative of tangent of x, if we can rewrite this trig function in terms of the others, so if we can rewrite tangent in terms of sines and cosines, then that's going to give us a way that we can be able to find the derivative of tangent without having to have it memorized. The only two that you actually have to have memorized are these two. And then if you can remember the identities of the others, then you can be able to find the derivatives if you need them. So tangent is sine over cosine. So this is the derivative of sine x over cosine of x. And this is where we can use the quotient rule to be able to figure out the rest of this. So if you don't remember the quotient rule, that says that if you have like some high function over some low function, the derivative of that is going to be low d high minus high d low all over low squared. So we are just going to be plugging in these different pieces. So here our low function is cosine and our high function is sine. So that means we can say that the derivative of sine x over cosine x is low d high, so low is cosine of x, times the derivative of our high function. The derivative of sine is cosine of x. Then we have minus high, so minus sine of x, times the derivative of our bottom function. So that's going to be a negative sine x, all over the bottom squared. So all over cosine squared x. So we get a cosine squared x minus negative sine squared x. So that's a plus sine squared x, all over cosine squared x. Cosine squared plus sine squared is 1. So this gives us a 1 over cosine squared of x, which is also equal to secant squared of x. So that's how we can find that the derivative of tangent of x is secant squared x. And we could do the same thing if you had the derivative of secant, the derivative of cotangent. You can rewrite them in terms of sines and cosines, and then you can just take the derivative using the quotient rule. So those other ones are going to be, let's see, so we got derivative of tangent of x is secant squared x. The derivative of secant of x is secant x tangent x. The derivative of cotangent of x is negative cosecant squared of x. And the derivative of cosecant of x is negative cosecant x cotangent x. The four that come up the most in the rest of calculus are going to be these first four. The bottom two don't show up super often, but they do show up occasionally. But the first four are the most important, but the first two are the only two that you actually have to memorize, because all of the others you can find using the quotient rule to be able to find any other derivatives. Did that answer your question? Does anyone have any other topics or questions that they'd like to go over? Okay. Let's see.
I have one.
Yeah, go for it.
I was just wondering if we can do like quotient product rules with sine and cosine, just like hard examples where you have to use trig identity.
Oh, yeah, we can go through some more of those. Okay. So another useful thing to know is there's not actually very many trig identities you have to have memorized. You can figure out most of them from just the same basic few. So if you can remember the sine of a plus b and the cosine of a plus b that we were using earlier, those are going to be the ones that come up the most often. So cosine of A plus B, that is cosine A, cosine B, minus sine A, sine B. We have sine of A plus B is sine A cosine B plus sine B cosine A. And then our last one is that sine squared theta plus cosine squared theta is equal to 1. These are actually the only three that I have memorized. The other ones I can figure out using these to figure them out. So for example, there is also the identity that 1 plus tangent squared theta equals secant squared theta. So I'm going to number our three equations. We have 1, 2, and 3. This last one, this is just taking equation 3 and then dividing everything by cosine squared theta. So 1 over cosine squared theta, that gives us the secant squared theta. Cosine squared theta over cosine squared theta, that's our 1. And then sine squared over cosine squared gives us the tangent squared. So you can figure that one out by dividing everything by cosine squared. If we had taken everything and divided it by sine squared, that would give us the other identity that we have 1 plus cotangent squared is equal to cosecant squared. That's where that identity comes from. Other ones that you can come across might be like sine of 2x is equal to 2 sine x cosine x. Well, this one is just sine of x plus x and then using equation 2. Other identities come if you have cosine of 2x. Cosine of 2x has several different ones. So cosine of 2x is cosine squared x minus sine squared x. So that's just if you plug in cosine of x plus x. But then if you combine that with equation 3, and for example, if you were to first solve equation 3 for cosine squared, then you would be able to get this is also equal to 1 minus 2 sine squared x. Or if you had solved for sine squared instead, you'd get 2 cosine squared x minus 1. All three of those are equal to cosine of 2x. And so those are some different things that you might come across. And then if you have these double angle formulas, you can then find the half angle formulas by replacing in these last two. You can replace x for like theta over 2. And then that's going to give you a way to be able to solve for your half angle formulas. So any of those identities can all be traced back to just these three. So if you're stuck and trying to figure out what identity can I use, if you can figure out how to write it in terms of these, that'll give you a good jump on how you might be able to approach that. But let's go and do a couple derivative problems. So let's say that we are trying to say that f of x is equal to sine squared x plus 3 cosine of x divided by sine x plus cosine x. And we are trying to figure out what is the derivative of f. So this is the quotient rule. So it's going to be low d high minus high d low all over low squared. So that's going to be our low function is sine x plus cosine x times the derivative of our top function. So derivative of the top, the derivative of sine squared, that's going to be a chain rule. So the derivative of sine of x squared, we are going to do, it's 2 times sine of x to the 1 multiplied by the derivative of sine of x, so times cosine of x. So that is a 2 sine x cosine x. So that is part of our d high. So let's see. So we got a 2 sine x cosine x. And then 3 times cosine of x. The derivative of cosine is negative sine. So that's minus 3 sine x. there is low d high. Now we need to do minus high d low. So minus high is sine squared x plus 3 cosine x. The low derivative of sine of x is going to be cosine x. Switch pens. Cosine x, and then derivative of cosine is negative sine x. So there is our entire top. We're going to put all of that over sine x plus cosine x squared. So at this point, we could probably leave it at this, or we could multiply everything through and hope that some stuff cancels or simplifies. So if we were to multiply everything through, this would give us, we have a 2 sine squared x cosine x minus 3 sine squared x. Then we have a plus 2 sine x cosine squared x, and then a minus 3 sine x cosine x. And then we have on the other side a minus, let's see, we have a minus sine squared x cosine x. We have then minus sine cubed x plus 3 cosine squared x and a minus 3 sine x cosine x. All over sine x plus cosine x squared. So if we distribute this negative through, that's a minus there, plus there, minus there, and then a plus there. We can then see if anything will combine. So let's see, so we have a 2 sine squared cosine and a minus sine squared cosine. So that gives us a sine squared x cosine x. So that takes care of that one and that one. Let's see. We have minus 3 sine squared plus, let's see, is that all of them? Oh, we have a minus 3 sine squared x and a minus 3 cosine squared x. So those two together can be combined to become a minus 3. Let's see, we got a plus 2 sine cosine squared, and that appears to be the only one. So plus 2 sine x cosine squared x. We got that one. We have a minus 3 sine x cosine x and a plus 3 sine x cosine x. So those just cancel. And then we have a plus sine cubed of x. So we have all that all over sine x plus cosine x squared. I would probably leave it at this point. I think that would be about as simplified as we could probably reasonably expect it to get. There is a way that you could probably combine these a little bit. And the way you would be doing that would be rewriting sine cubed of x as sine x times sine squared x. And then you'd be able to combine it a little bit with this cosine squared x term. That would be a way that you might be able to combine them. But I would probably leave it at this point. That is probably a reasonable spot to expect you to be able to stop. Going past that would probably require you to know where you're supposed to end up and then figure out what substitutions and stuff to make to be able to make it work. And if you're stuck at that point, and that is actually what you're asked to do, what I would recommend doing is write down these different identities and then figure out, going both forwards and backwards, how to get it to meet in the middle somewhere, and just try and work with that if that is what you are asked to do. Okay, did that answer your questions with that, or would you like to see a couple more? Okay, does anyone else have any other topics they'd like to go over?
Can we do some of the chain rule? Can we do some of the chain rule?
Yeah, we can do some chain rule. All right, so let's say Here, let's just go all out with the chain rule. So let's say the f of x is, we have cosine cubed of sine of x squared plus 6. Come on, draw the 6. There we go. 6, 7x plus 2 cubed. Oh, we already have a cubed. Let's make that to the 4th. So let's say that that is our f of x. Let's try and figure out what is our f prime of x. We need to figure out what is that equal to. A helpful thing to do might be to rewrite this just a little bit to make it a little bit more clear what the nested functions are. So if we were to do that, we could rewrite our function f of x as cosine cubed is cosine of sine of x squared plus 6 times 7x plus 2 to the 4th, all cubed. And so our outsidemost function is going to be this fact that we have a cubed on the outside. So that means that our derivative, f prime of x, and I'm going to try and use some nested colors. So our outsidemost one is going to be this 3. So that means we are going to bring the 3 down, and then that is going to be multiplied by everything on the inside without changing it, and then we decrease the power by 1. So that means the inside is going to just be cosine of sine of x squared plus 6 times 7x plus 2 to the 4th, all of that squared. But then we need to multiply it by the derivative of this inside piece. Now that function is going to be this cosine. So the derivative of cosine is going to be, we have a negative sine of the inside, which then is not going to change, and that's going to be what that piece is going to go to. So that inside piece is going to be, that does not change, so that's going to be a sine of x squared plus 6 times 7x plus 2 to the 4th. Now the question here is, now we're going to have to be multiplying by the derivative of the inside of that. And this function is combined by an addition sign. So that means we are going to take the derivative of the first piece and then add the derivative of the second piece. So that is then going to be multiplied by, let's see, already did that color, let's do purple. So sine of x squared, we have a sine of x squared. So that derivative is going to be, the derivative of sine is going to be a cosine, and that's going to be cosine of x squared, but then we need to multiply it by the derivative of the x squared. So that's going to then be multiplied by a 2x from that piece. And then we are going to be adding to that the derivative of this other side. So that is going to be a 6 times the 4 of the 7x plus 2 cubed. And that is going to be multiplied by the derivative of this inside piece, the derivative of the 7x plus 2. The derivative of that is going to be just a 7. And now we have completed the chain rule problem. We have gone all the way in through all of the different functions that were nested together. And this absolute mess of a function is the derivative. I would not try and combine things a bunch. I might move the negative sign here out to the very front and then rewrite this 6 times 4 as just 24. But other than that, I would not try and simplify this at all. Oh, maybe move the 7 into the 24 as well to make that whatever that multiplies to be. But that would be about where I would stop. I wouldn't try and use identities to make this rewrite nicer because odds are it probably won't work very well. Once you get to this point, combine constants and move a negative to the front if it is there, and that is probably a good place to stop. Would you like to go through a like slightly easier chain rule problem, or would that be good for you?
We can go ahead and do another one if that's okay.
Yeah. So let's say that we have f of x is equal to, let's say it is the square root of sine squared of x cubed minus 7x plus 16. Oh, I should not have square root of sine squared. That makes it a little easy. Plus 2. There we go. That makes it so we don't just cancel all the square root and the sine. Okay, so the derivative of our outsidemost function, so our outsidemost function is going to be the square root. So f prime of x, so the derivative of the square root of x is 1 over 2 times the square root of x. You can get that either by remembering that, or you can rewrite the square root of x as x to the 1/2, which then means that the derivative of that is going to be a 1/2 x to the 1 minus 1/2, or x to the minus 1/2. So I'm going to use this form up here at the top, just because that looks a little cleaner. So that means our derivative is going to be, we have 1 over 2 times the square root, and what's inside the square root from the chain rule does not change. So sine squared of x cubed minus 7x plus 16, close parenthesis, plus 2. And then we are going to multiply that by the derivative of the inside. So the derivative of the inside is going to be a chain rule problem, because the derivative of sine squared, well, that's going to have a chain rule piece come out. So that is going to be, so sine squared, we can rewrite the sine squared as sine of that squared. So that means we are going to be multiplying by 2 times the inside, which is not going to change. So sine of x cubed plus, x cubed minus 7x plus 16, and then raised to the 1. So that's the derivative of the inside, because the derivative of the plus 2 goes to a plus 0. So we technically have a plus 0 right there. And so then we need to multiply this term. We need to multiply that by the derivative of the inside function, which in this case is going to be sine. So it's then multiplied by the derivative of sine is cosine. So times cosine of, and the inside doesn't change, x cubed minus 7x plus 16. Then multiplied that by the derivative of the inside, which gives us a 3x squared minus 7. And that's going to be what our derivative would be. In this case, we could cancel this 2 and this 2, and then I would take all of this stuff and just stick that on the numerator and call that good. Any other questions that people have?
So all that is the part on the bottom with circles and the fraction and row circled spots, that's the answer.
Yeah. So with the chain rule, if you have like f of g of h of x, the derivative of that is just going to be f prime of the inside not changing, so g of h of x, multiplied by the derivative of the next function. And you just keep nesting it however long you have to go until you eventually, derivative of x is just a 1. As soon as you get to that point, you know, okay, I finished that chain, and so I can continue on with the rest of my problem. So it doesn't matter if you have 1, 2, 3, or 10 functions nested. As long as you can like keep track of what function's next, you can be able to take the derivative of really, really nasty functions like this first one that we did up here. Like you're able to take those derivatives because it follows that same fairly straightforward pattern. It might not always be super clear which function is which, and that's part of why writing it very carefully in a specific way can help. This sort of thing that I was doing up here where I was underlining things, that's something that I do in my Scratch work as well when I'm working on a problem, just to make sure that I know, okay, which function is the next function I'm going through and working on, so that I can be able to take the derivative and remember all the different pieces in the order that they're showing up.
Can we possibly do the chain rule with with E?
Oh, yeah, we can definitely do some with E. All right, so let's say that we have f of x is equal to tangent of e to the x cubed plus 5x. So our first function, so our outsidemost function is tangent. So the derivative of tangent is going to be secant squared. So we got a secant squared of, and the inside does not change, e to the x cubed plus 5x. Then we're going to multiply that by the derivative of the next function. The next function we have is this e to the x cubed plus 5x. So our next function is e to something. So the next one is the derivative of e to the x. So that is just going to be e to that stuff left alone on the inside. So x cubed plus 5x. Then multiplied by the derivative of the inside of that, which is a 3x squared plus 5. And so that is going to be our derivative of f prime of x. Yeah. Are there any other functions anyone would like to throw in to have in the chain rule, or other types of problems people would like to see? Let's see. I believe implicit differentiation is on your test, or is that next section? Implicit
it's on the next section. It's on the next section.
Okay. Okay. Because I know that's often combined with the chain rule. I just didn't know if that was in the same test or if that was barely missed out on this test.
Can we do 70 sine of PT?
Huh?
70 sine PT. Like 70. Okay, so let me phrase that. 7x times sine of pi x.
So taking the derivative of this?
Mm-hmm.
Yeah, we can take the derivative of this. So if f of x is equal to this, and we are trying to find f prime of x, the first thing I would notice is I would rewrite this as 7x times sine of pi x. And so now, once we've written it that way, it becomes a little bit clearer that this is going to be a product rule piece.
Mm-hmm.
So the product rule says if you take the derivative of f times g, this is going to be f prime g plus f g prime. And so if we just follow this formula, that's going to give it to us. And then sometimes we might need to use the chain rule or the product rule to figure out either f prime or g prime. So in this case, we might get something like, so f prime, so the derivative of 7x, that's just 7. And then g doesn't change, so that's sine of pi x, plus f, so plus 7x times g prime. Here, to find g prime, we're going to have a chain rule. So our outsidemost function is sine of something. So the derivative of sine is cosine. So inside does not change. Multiplied by the derivative of our inside. So our inside function is pi x. The derivative of that is going to be a pi. So f prime of x is going to be 7 sine of pi x plus 7 pi x cosine of pi x. That's going to be what our f prime would be. Other times that we might have it is you might come across like a chain rule where you have to have a product rule piece. So for example, you might have something like, let's say we have secant of e to the x sine x. So if this is our function f of x, then f prime of x is going to be a chain rule first off, because we have our outsidemost function is secant. So that goes to a secant of the inside, tangent of the inside without changing those, e to the x sine x, e to the x sine x, multiplied by the derivative of the inside. Here we have e to the x times sine x. So we have f prime g plus f g prime. So f prime is e to the x. Let's not use that color. So we got e to the x times g sine of x plus f e to the x times g prime. Derivative of sine is cosine. And so that is how we would be able to take this derivative. So chain rule, product rule, quotient rule, all of those are things that can show up nested inside each other. For example, your teacher might give you something which hopefully they don't, but it is possible. Maybe you're given something like f of x equals cosine of x squared e to the 2x divided by e to the sine of 1 over x. This is a perfectly valid function you might be asked to find the derivative of. You have a quotient rule, and then inside that quotient rule, you're going to have chain rules and product rules and other chain rules. And so this is something that you might be asked to find the derivative of. And if you were, just break it up into the different pieces. So the first thing we have in this case is we have a quotient rule. So if we were to figure out what the derivative of this would be, we have our quotient rule is low d high minus high d low all over low low. So the denominator, since that doesn't have any derivatives, not derivatives, any derivatives, we can just square the bottom. So the bottom squared is going to be e to the 2 sine of 1 over x. So that's the easy part of the quotient rule. We have, on the top, we have low d high. So low is e to the sine of 1 over x. D high, this is going to have a chain rule come in. So the derivative of the top is going to have a sine come out, because we need to take our outsidemost function is cosine. Derivative of cosine is negative sine. So we have a negative sine of x squared e to the 2x multiplied by the derivative of x squared e to the 2x. Here we're going to have a product rule. So our first function is x squared, so the derivative of that is a 2x. So we have a 2x e to the 2x plus x squared times the derivative of e to the 2x. Now, e to the 2x, that's also going to have a chain rule. It's going to be e to the 2x multiplied by the derivative of 2x, which in this case is just a 2. So that has now finished the derivative of the top. So that is our low d high. Now we have minus, we are going to have high and then d low. So our high function is just cosine of x squared e to the 2x. And then d low, we are going to have a chain rule. So let's zoom out a bit. And I thought I was ambitious enough with that length to start of a fraction line. Okay, so let's see. Derivative of the bottom, our first function is e to something. So that means we are going to have the derivative of that. The derivative of e is e raised to that without changing it. So e to the sine of 1 over x. multiplied by the derivative of that. So the derivative of sine is a cosine. So we have a cosine of 1 over x multiplied by the derivative of 1 over x. You can either do a quotient rule on that one, or you could recognize that as x to the minus 1 to then be able to get that your last derivative is going to be times a negative 1 over x squared. And there we go. We have successfully finished the quotient rule. So even though that problem looked an absolute nightmare, it was not overly awful, I would say. Like, it's still a mess, but it is doable. If you can recognize each piece, I can just break up into what do I need to work on right now. We know we have a quotient rule, so it's going to be low d high minus high d low all over the bottom squared. Well, we know low, we know high, and we know the bottom squared. All that we have left is what's the derivative of the top. There we had to use both the chain rule and the product rule. What's the derivative of the bottom? We had to use the chain rule and the quotient rule. But each piece is doable on its own. So just work on each piece one at a time, and then you can go through and break it up piece by piece. If this is something that was like a bit hard for you to follow, what I would maybe recommend is rewrite f of x. So say f of x is equal to high over low, and then just say high is just the cosine of x squared e to the 2x. Low is just e to the sine of 1 over x. And then you could say, well, I know for a fact f prime is going to be low d high minus high d low all over low squared. And then you can plug in everything that you know. So we know low, we know high, we know low squared. Now we just need to figure out what's the derivative of the high, what's the derivative of the bottom. You can compute you can compute those somewhere else on your paper and figure them out, and then you can plug them back in. So you can take each problem and break it up into smaller pieces, and then you can deal with those separately. Any other questions or topics people want to go over?
I have one. I'm trying to remember what it's called, so I'm kind of just zooming from it. It was asking like if we actually worked on this together. It was saying if g of x was like x over e to the x, find g to the n. I
Yeah.
have examples of that because I'm not very used to it.
Yeah, patterns of finding finding patterns.
And once we did that, is it okay if we do a little bit with infinite limits? And once we did that, is it okay if we do a little bit with infinite limits? Great, thank you.
Yeah, we can do some infinite limits.
Great, thank you.
Yeah, okay, so let's say that we have f of x is equal to, let's say it is x squared e to the 3x. And we're trying to figure out a pattern for our derivatives. So if we look at our first derivative, let's just compute what that is going to be. So we have a product rule. So we get a x squared e to the 3x times 3 plus 2x e to the 3x. So this is equal to 3x squared e to the 3, come on, 3x plus 2x e to the 3x. So far, I'm not seeing a pattern. Oh well, let's continue. Take our second derivative. So we get 3 times what we started, because 3x squared e to the 3x, that's going to just go to a 3 times this again. So 3x squared e to the 3x plus 2x e to the 3x plus the derivative of 2x e to the 3x. So 2 times x e to the 3x first times the derivative of the second plus the second times the derivative of the first. So this gives us 9x squared e to the 3x plus 6x e to the 3x plus 2x e to the 3x. Oh, whoops, nope, that's not 2. That's 2 times 3, so that's another 6. and then plus 2e to the 3x. So this is 9x squared e to the 3x plus 12x e to the 3x plus 2e to the 3x. At this point, I'd try and figure out, is there any pattern that I'm spotting? One pattern I am seeing is that if we look at just the x squared e to the x term, so we have 9x squared e to the 3x, 3x squared e to the 3x, and then 1x squared e to the 3x. Those are powers of 3. So that tells me that odds are looking pretty good that my guess for what our nth derivative of x is going to be, I am going to go out on a limb and say that I'm thinking there's going to be a 3 to the n x squared e to the 3x. I think that is going to be part of it. And so once I've done that, I can then basically ignore that term if it continues to be matching as I'm taking other derivatives. So we're able to slowly be breaking down the number of things we're having to take derivatives of. The other one we have is we have 0x e to the 3x in the first one, then we have 2x e to the 3x, then we have 12x e to the 3x. So we know we're going to have an x e to the 3x and then a constant e to the 3x. The only question is what constants are going to be out front. So those are now what we're trying to figure out. We're trying to figure out what's the pattern in the constants. So if we were to compute what's our third derivative of f, well, that's going to be, we have 9 times the derivative of x squared e to the 3x. So that gives us a 9, 3x squared e to the 3x plus 2x e to the 3x. Then we have plus 12, the derivative of x e to the 3x. We already computed that. 3x e to the 3x plus e to the 3x. And then the derivative of e to the 3x is going to just be 3e to the 3x. So 2 times 3e to the 3x. So when we compute these, we are going to get 27x squared e to the 3x, which is good because that's matching the pattern that we spotted so far. Then we have plus 18x e to the 3x, and then we have plus 36x e to the 3x. So let's see, 18 plus 36, that's 44 plus 10, that's 54. So 54x e to the 3x. And then our e to the 3x's, we have 12 plus 6, so 18 e to the 3x. All right, so at this point, we're not really seeing a pattern, or at least I'm not. If you are, congratulations. This test will be much easier for you than it would be for me. But I'm not seeing the pattern right now. So let's go and just look at those coefficients to see if we can start to spot some potential patterns. So if we are looking at our x e to the 3x term, and we are looking at our different n values. When n is 0, in other words, in our original function, the coefficient of x e to the 3x is 0. In our first derivative, the coefficient is 2. In our second derivative, the coefficient is 12. And then in our third derivative, the coefficient is 54. So these are not looking like there's a super easy pattern to spot. And so at this point, what I would recommend doing is factor the numbers. So 12 is 2 times 2 times 3. So this is 2 times 2 times 3. And then 54, that is 9 times 6. So that's 2 and then 3 3s. And so one thing I'm noticing is there is always a 2 in there. And then we went from 1 3 to 3 3s. Whoa, what happened? All right, so we went from 1 3 to 3 3s. So I'm guessing there's going to be increasing number of 3s. My gut is saying that it's going to be like 1 3, then 2 3s, then 3 3s, which means I'm trying to figure out what on earth is this 3 doing. I don't know where that's coming from. And so I'm going to need to go through at least one more derivative to figure out what the pattern is going to be. So let's go through and figure out what is our fourth derivative to hopefully find a pattern here. So that's going to be 27 times 3x squared e to the 3x plus 2x e to the 3x plus we have 54 times 3x e to the 3x plus e to the 3x plus 18 times e to the 3x. So let's see. So we got 81 x squared e to the 3x plus 54 x e to the 3x plus another 3 times 54. So that's 4 times 54. That is 216. Let's hope we find the pattern soon. Let's see. Then we have 54 plus 18 e to the 3x's. That is 72 e to the 3x. So 216 is 6 cubed.
I think it's 162. I think it's 162. Yeah.
162?
Yeah.
Let's see. We got 54 plus got that one, and then 162. Yeah, it's going to be 216. This term is 162, but then the 27 times the 2x e to the 3x gives us another 54 of them.
Oh, I see what you mean. Okay, thank you.
Yeah, so that 3, 3, 3. Okay, so the fact that we had 3 3s this time makes me a lot more confident that we are going to have increasing number of 3s by 1. The question now is, what is this like 2, 2, 2, 2, 3, 2, 2, 2? What is that doing? So since there's always at least one 2, this is, I'm going to pull out one of these 2s from everything. Because we got those, my gut is saying that there's always a 2 in there, so I'm going to just pull that 2 out and see if I can find a pattern in what's left. And if we look at what's left, it goes 2, 3, 4. And so at that point, I'm like, oh, that looks a lot like a pattern. So my guess is that there's going to be a 2 followed by, let's see, it's when n is 2, it's 2. When n is 3, it's 3. When n is 4, it's 4. So it's going to be 2 times n times 3 to something. When n is 2, we have 3 to the 1. So it's 3 to the n minus 1. So 2n, 3 to the n minus 1, that is going to be what we have right here. So it's 2n, 3 to the n minus 1. And that is the pattern that we have for our x e to the 3x's. And now we just need to figure out what's our pattern for just our e to the 3x's with our different n values. So when n is 0, we have 0 of them. When n is 1, we have 0 of them. When n is 2, we have 2 of them. When n is 3, we have 18 of them. And when n is 4, we have 72 of them. So again, we're not seeing a pattern here directly. So we're going to, again, break this up and factor them. So 18 is 2 times 3 times 3. And then 72 is 6 times 9. So that's 2 and 3 3s. No. 72 is 8 times 9. So 3 2s and then 2 3s. 2, 2, 2. All right, so again, this is looking pretty similar to what we had last time, where we had a collection of 2s that was showing up in everything. So we have a 2 in the front of every term. And then we have like some 3s that would show up. So like pairs of 3s, and then it goes 3, 4. So to me, it's looking like we might be having just a 2 n and then 3 to the n minus 2. And so that's what it's looking like to me, but it might not be that straightforward. So let's look at just one more to make sure that that pattern is actually holding. And if it doesn't, then we're going to need to change our minds and find a different pattern that also works. So unfortunately, that means we have to take another derivative. So our fifth derivative is going to be, we got 81 times 3x squared e to the 3x plus 2x e to the 3x plus 216 times 3x e to the 3x plus e to the 3x plus 72 times 3. Wait a second. Our fourth derivative, I think, is incorrect, because we forgot to take the derivative of this e to the 3x. There should be a 3 in front of that, which means that our pattern that we saw is not going to be a valid pattern. So that was 2 times 3 times 3. But then this is 8. This fourth derivative should be 18 times 3e to the 3x. So we have 54 plus another 54. So that should be 108. So 108 is 12 times 9. So that's 2 2s and 3 3s. 2 times 2 times 3 times 3 times 3. Yep. That's what that one is. So then our fifth derivative is not 72 times 3e to the 3x. It's 108 times 3e to the 3x, which means we are going to get 243x squared e to the 3x plus 2 times 81, 162 x e to the 3x plus 216 times 3. This is now at the point where I don't want to do mental math. So let's see what that would be. 216 times 3 is 648 x e to the 3x. Plus 216 e to the 3x plus 108 times 3 is 324. All right, so our guess is no longer good. So let's see, what is all of that equal to? So that is 243x squared e to the 3x plus 162 plus 648 is 810 x e to the 3x plus 216 plus 324 is 540 e to the 3x. Let's hope that we can factor that one. Let's see, so 540 has a 5 in it. So 540 divided by 5 is 108. So we can put in 2 2s in there. So there's 2 times 2. And then we're left with 27, so that's 3 3s. So there's our fifth one. So that is making it a bit harder to try and figure out what that pattern is going to be. So we do have a 5 showing up. So right here, this 5 is making me guess that there is going to be some sort of n showing up in there. So if there is an n, so if our guess of having an n shows up, that means we need to get a 5 out of there, this 2 times 2 from the 4, and that 3 from there, and then this 2 from there. And so now we have to figure out what are we doing with the rest of these terms. So we have, so the remaining terms are we go 0, 0, 1, 6, 9, oh no, not 9, 27. And then 27 times 4 is 108. So that is not super clear as to a pattern in that part. Let's see. Another thing is hopefully we still have that consecutive powers of 3 dealing going on. So we have 3, 3 squared, 3 cubed. And then at this point, what we're left with is 2, 3, 4. And so that's telling us that that is a fairly strong looking pattern. So we have an n, and then the 2, 3, 4, that's an n minus 1. So we got n minus 1, and we have powers of 3, and this is going to be 3 to the n minus 2. So we have n minus 1, 3 to the n minus 2. And so there is our pattern. A lot of this is just trying to recognize what are things that I think are patterns and try and pull those out and see, does that leave me with more pattern stuff that's showing up? So here, grabbing the 5, once we got to the 5th derivative, we saw that 5, and since 5s hadn't shown up anywhere else, that gave us a strong guess that, okay, there's probably something involving n in there. Then once we pulled that out, we were like, okay, we have 2 3s, 2 3s, 3 3s. So 2 3s and then 3 3s, that says maybe there's just consecutive powers of 3, which is something that was suggested every time we were taking a derivative, because we had 3e to the 3x, 3e to the 3x. It looked like we were multiplying by 3 fairly frequently. So pulling out 3 to something is probably going to be fairly common. And that happens a lot anytime you have like an e to the 3x, you're probably going to have 3 to the n's in your pattern. E to the 5x is probably going to have 5 to the n's in your pattern. So once we pulled that out, then we looked to see what do we have left. We had a 2, we had a 3, and then we had 2 2s. And so that was a 2, 3, 4 pattern again. So we probably had an n minus 1 showing up. And so that gave us all the tools we needed to figure out what our pattern was. And so we can put all of those together to say that our entire pattern says that our nth derivative, let's make that bigger. So we can put all of that together to say that our nth derivative of f is equal to 3 to the n x squared e to the 3x plus 2n 3 to the n minus 1 x e to the 3x plus n times n minus 1 3 to the n minus 2 e to the 3x. And so that's how you might be able to go through and find a pattern like this. On a test, it's unlikely that they would give you like an x squared in the pattern if they were multiplied. If there was a division, then that might be something that they would do. If they were multiplied, it would probably just be like an x e to the x or x e to the 3x sort of pattern. And then division, you might see those sorts of things coming up as well. Was that a good example?
Yeah, a little overall.
Yeah, a little big, probably should not have had the x squared. But like each piece is not too bad. Like
how did you get for the first part at least, how did you get the 2 times n times 3 to the x power of n minus 1?
Yeah, so for this first one,
because your 2 is because you pulled out the 2.
Yeah, so we pulled out the 2.
And your 3 is because it's times in it by itself, right? 3. And Is it because it's 1, 2, 3, 4? Is because that's your n? Is that what
Yeah, that's because those matched up with n. So we had a 2 when n was 2. We had 3 when n was 3, and we had 4 when n was 4.
Okay.
So that's how we knew it was n. And then in our second one down here, what we had was so our blue circles was 2 when n was 3, 3 when n was 4, and 4 when n was 5. Mm-hmm. So it was 1 less than n. So that's where this n minus 1 came from.
Kind of same. The 5 just went along with like 2, 2, 3, 3, 4, 4, 5. Got it.
Yeah, and when we noticed we had the 5 when n was 5, that was a strong suggestion that, okay, 5 with 5 probably means there's an n. So once we pulled out n and n minus 1, then we were seeing that we had the 3 to the n minus 2 showing up as well.
Okay, yeah. And yeah, you subtracted it by 1 with n in the first power because it just like, is it because it didn't go along right next to each other? Like.
Yeah, so for example, in the one we're looking at here, so for our second part, when we figured out we had 3 to the n minus 2, that was because we had a 3 to the 1 when n was 3. So it was 3 to the 1 here. Then we had a 3 to the 2 for n equals 4, and then a 3 to the 3 when n was 5. So the power was just always 2 less than n. Okay. And then our example above it, our powers of 3 were just 1 less than n. And so that's how we were getting those different pieces.
Yeah. Okay, that makes sense.
Okay. Infinite limits. Like limits at infinity or limits when they are equal to infinity?
Can we do limits at infinity? Can we do limits at infinity?
Mm-hmm. Yeah, so let's look at the limit as x goes to infinity of 3x squared plus 2x divided by 5x squared plus 7. So if you are dealing with a polynomial, what I would recommend doing is just divide the top and bottom of the limit by the highest power of x, anywhere that shows up anywhere. So in this case, our highest power of x is x squared. So we're going to multiply the top and bottom by 1 over x squared. This is a technique that'll almost always get it to a nicer place. So once we've done that, this becomes the limit as x goes to infinity of 3 plus 2 over x divided by 5 plus 7 over x squared. And at this point, we can rewrite this as equal to the limit as x goes to infinity of 3 plus 2 over x divided by the limit as x goes to infinity of 5 plus 7 over x squared, which is equal to a 3 over 5. So that technique is something that'll work anytime you're dealing with polynomials on the top and bottom. So another one that you might see might be something like the limit as x goes to infinity of 7x cubed plus 4x divided by 2x squared plus 6. Here, if we divide the top and bottom by the highest power of x, so 1 over x cubed, 1 over x cubed, what we are left with is we get the limit as x goes to infinity of 7 plus 4 over x squared divided by 2 over x plus 6 over x cubed. And so this one is going to be 7 over plus or minus 0. So we know it's going to be one of the infinities. In these sorts of situations, you can also, so you could either always divide by the highest power of x, or you could divide by the highest power of x in the denominator. In this case, dividing by the highest power of x in the denominator will give you an easier limit to do. So if instead we had multiplied the top and bottom by 1 over x squared, this would give us the limit as x goes to infinity of 7x plus 4 over x divided by 2 plus 6 over x squared. And then this limit, it's very easy to see that this bottom piece is going to 2, and this top piece is going to infinity. So we have infinity over 2, so this limit is equal to infinity. And so that's the sort of techniques that I use when I am doing limits with fractions, and we have a polynomial in the top and bottom. Are there other sorts of limits that you would like to go over?
How would you know if the infinity was a negative or positive?
Mm-hmm. Yeah, so in this case, we have infinity over 2. Both of those are positive, so it would go to positive infinity.
Or like the second one's a negative,
Yeah, if it was like a negative 7x or over a negative 2, then it would go to a negative infinity. Because one is positive, one is negative. That's when it would go to positive infinity. And that's why this top limit was a bit harder to figure out. Because this is a 7 over 0. The question is this 0 a plus or a minus?
So if one of them's negative, it's still positive? So you just said?
No, so if one is positive and one is negative, then it's negative.
Yeah.
So basically it follows the same general rules, like negative divided by negative is positive, positive divided by positive is positive. You just have to figure out anytime you're dividing by 0 or 0, anytime you're dividing by 0, the question is it going to be positive or negative infinity?
Yeah.
And in this case, that's why dividing by the biggest power in the denominator gave a nicer limit, because we didn't run into that question.
I have a question. So our math teacher told us about the shortcuts.
Our math teacher told us about the shortcuts for like looking at the powers
of the highest powers,
or the coefficient of the highest powers.
If it's on the test
those limit
and
rules,
we use
if
that
it's on the
method,
test,
is that like a valid method to get to an answer, or do we need to do the writing out like this to get
an answer, or do we need to do the writing out like this to get full credit?
So I'm not sure on the grader. That shortcut method is actually what we're doing right here. So if you want to do that shortcut method, you could just add this like one step right here, get this limit, and then you're able to just evaluate it directly. So if you want to be safe, I would do it this way, but that shortcut method is going to be working. And this is the logic as to why that shortcut method works. Yeah. Any other questions with these?
We're good. We're good.
Okay. Any other topics people would like to go over?
Can we do the limit of like x pushing 0 with trig?
Like limit as x goes to 0 of cosine x minus 1 over 2x squared?
Yeah, something like that. It's literally in my homework. Yeah.
Okay. Yeah, so if we were to come across something like this, our goal is to end up, whoa, that is thick now. So our goal is to end up with one of these two limits, either the limit as x goes to 0 of sine x over x, which is equal to 1, or the limit as x goes to 0 of cosine x minus 1 over x, which is equal to 0. So looking at this limit, we might say, okay, cosine x minus 1, we are going to want this second form. So let's try and write this so that we have that second form coming up. So that gives us the limit as x goes to 0 of 1 over 2x times cosine x minus 1 over x. So limit rules then say we can break this up into two multiplications. So this is equal to the limit as x goes to 0 of 1 over 2x times the limit as x goes to 0 of cosine x minus 1 over x, which gives us positive or negative infinity times 0. This is an indeterminate form. This is something that could literally be any number. Depending on the circumstances, this could show up to be any different number that we could possibly think of. And so that tells us that that was not the right way to go about it. So just substituting cosine x minus 1 over x did not get us to something that we could evaluate, which tells us somehow we need to use this other limit in our problem. So we need to convert the cosine x minus 1 somehow into sines. And so what we can do is we can try and go back to what identities involve cosines and sines. Well, the main identity that we can remember is that sine squared x plus cosine squared x equals 1. So if we were to maybe subtract the 1 over, we'd get cosine squared x minus 1 is equal to negative sine squared x. Cosine squared x minus 1 is pretty close to cosine x minus 1. So if we can somehow multiply that by something to turn it into a cosine squared x minus 1, that'll give us a way to be able to approach this problem. So you might remember that if you have x squared minus 1, this is equal to x minus 1 times x plus 1. So since we have a cosine x minus 1, let's multiply everything, so the top and bottom, by cosine x plus 1. So we have the limit as x goes to 0 of cosine x minus 1 over 2x squared multiplied by cosine x plus 1 over cosine x plus 1. This is the limit as x goes to 0 of cosine squared x minus 1 over 2x squared times cosine x plus 1. At this point, let's replace the cosine squared x minus 1 with the negative sine squared x. So this is the limit as x goes to 0 of negative 1 times sine squared x divided by 2 times cosine x plus 1 times x squared. Now what we can do is our goal was to get sine over x. Here we have sine squared x over x squared. So we are going to break this up into some multiplications. So this is equal to the limit as x goes to 0 of negative 1 over 2 times cosine x plus 1 times sine x over x times sine x over x. And while we technically would need to break this up and stick a limit right here and then a limit right here, we know that this term goes to 1 and this term goes to 1. So this is equal to the limit as x goes to 0 of negative 1 over 2 times cosine x plus 1, which is equal to a negative 1 over 2 times cosine of 0 plus 1. So a negative 1 over 2 times 1 plus 1 equals a negative 1/4. And so that's how we would be able to tackle this problem. We remember that there are these two limits that are useful to be able to know. So sine x over x goes to 1. Cosine x minus 1 over x goes to 0. If one doesn't work, try and find a way to use the identity sine squared plus cosine squared equals 1 to hopefully turn it into the other one, and then try and get stuff to cancel out and be able to get to a number result.
I'm just curious, we didn't learn this yet, but I'm learning just to check if our answer's correct. Can we use L'Hopital's rule?
Yes, we can definitely use L'Hopital's rule to check this. Okay. So if you don't know L'Hopital's rule, you will be covering that in this class. That says that if you have the limit of, as x goes to something, of f of x over g of x, and if this is infinity over infinity or 0 over 0, this is equal to the limit as x goes to a of f prime of x divided by g prime of x. So in this example, you could have definitely used L'Hopital's rule to figure this one out. So we'd have limit as x goes to 0 of, let's see, it was cosine x minus 1 over 2x squared. If we just plug in 0, we get 0 over 0. So this is in a valid form to use L'Hopital's rule. So the derivative of the top, derivative of cosine is sine.
Negative sine.
Yeah, negative sine. So that's negative sine of x all over 4x. So again, you plug in x equals 0, you get 0 over 0. So it's still in a form where we can use L'Hopital's rule again. So then take the derivative of the top and the derivative of the bottom. The derivative of the top becomes negative cosine of x. Derivative of the bottom just becomes 4. You plug in 0, you get negative 1/4. So you can use L'Hopital's rule to check, but since you haven't used it, you should not use this as your primary method on the test. But this is a way that you would be able to check or figure out what am I even trying to get to. So if this made sense to you, feel free to use it to check your work. If it didn't make sense or you don't feel comfortable, don't use it because you will learn it later and it's not something that is required for this test. Yeah. Any other questions that anyone has?
I have a problem that I'd like to go over.
It's
find a value c such that the line y equals 2x plus 3. Tangent to the parabola y equals cx squared.
Tangent to the parabola y equals cx squared. I can repeat any of that if you need me to.
Okay, so y equals 2x plus 3.
The parabola y equals cx squared.
The parabola y equals cx squared.
Okay. Okay. So for something to be a tangent line, we have to have two conditions be satisfied. First, they have to intersect. And then second, they have to have the same slope. So if they intersect, that tells us that we need cx squared to be equal to 2x plus 3. We need them to both pass through the same point. So that's one condition that is required in order for them to intersect. And then second, for the same slope, we need to take the derivative of both functions and set those equal to each other. So I'm going to say that this first function is y1 and the second one is y2. So that means that we need, come on, switch color here. So that means that we need y1 prime to be equal to y2 prime. So y1 prime, the derivative of 2x plus 3, that's just a 2. But then the derivative of cx squared is 2cx. And so once we have these two equations, that gives us a way to be able to solve for c, because we have two unknowns and two equations. We don't know c and we don't know x. We have two equations, we can solve for those. So from the second one, we can find that that means that if we divide everything by 2c, we get x equals 1 over c. And so that means we can take that and plug that into this other equation. So we get c times 1 over c squared equals 2 times 1 over c plus 3. C times 1 over c squared, that's just 1 over c equals 2 over c plus 3. Which tells us that 0 equals 1 over c plus 3. Which means that negative 3 equals 1 over c, so c equals negative 1/3. And then what we could do is then that tells us that if we go back here to figure out what x is, we find that x is going to be negative 3. And then we can just check that this is actually the valid solution. Otherwise, we know we messed up somewhere. So if we look at, so we got y equals 2x plus 3, and y2 equals negative 1/3 x squared, the derivative of y2 is going to be a negative 2/3 x. And so if we plug in x equals negative 3, y2 prime at negative 3 is equal to positive 2, which is actually equal to y1 of negative, y1 prime. So the derivative of 2x plus 3 is 2. So the same slope term matched. And then the intersection, we just plug in the same value of x to see if it works. So y1 of negative 3, that is 2 times negative 3 plus 3, negative 6 plus 3 is negative 3. And then y2 of negative 3 is negative 1/3 times negative 3 squared, negative 1/3 times 9, which is equal to negative 3. So they both have the same intercept. And so that tells us that this is actually the tangent to negative 1/3 x squared.
Yes,
did I answer your question?
Yes, thank you.
Welcome. Any other questions that anyone has? All right. Well, if you don't have any other questions, I will wish you all the best of luck on your test. Feel free to come into the math lab if you have other questions tomorrow, or just find other topics that you're just not sure about. And I will be sticking around until 7, since that is how long I am supposed to be here. So if you do have other questions, feel free to stick around and ask them. But if not, good luck on your test.
Thank you.
Thank you.
Thank you.
Thank you. Thank you.
So our test is covering from 2.6 to 3.4.
Okay.
And so I feel like 3.1, 3.2, and 3.3, and 3.4 I've got, because that's kind of what we just covered.
Mm-hmm.
I'm trying to go back and go through 2.6, 2.7, 2.8. They all seem straightforward. It's just like, it's just like simple stuff of trying to find the vertical and horizontal asymptote, and then derivative and rate of change. It's just stuff I should probably review. Can we just like maybe go through stuff like that?
Yeah, we can go through some of those. Yeah, so
On sketching the derivative, I've always struggled with that.
okay. So let's say that our function, this is f of x. So that is our function f of x. Well, let's go through and figure out how can we plot f prime of x. So the way that I would go about doing this is I would first figure out where is f prime of x equal to 0. Well, we have f prime of x is horizontal there, 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 and there. So that means that at each of those points, we know that our f prime is going to intersect the graph. Whoops. Oh, go back. There you go. So it's going to look something like that. We also know that if it is sloping up, it's going to be a positive, and then if it's sloping down, it's going to be a negative. So that means that over here, it is some positive value, and it's staying about the same positive value, but then it's slowly decreasing until it rapidly hits 0. Then it's negative, and actually gets down to maybe about like -1, and then goes back up. And then it's positive, stays about the same slope for a little while, but then it goes back down, gets very, very steep downwards, and then very quickly levels out towards flat. And then from here, it's going to be increasing, gets to a pretty steep slope, but then it starts to decrease slope. And then it looks like it's getting close to 0, but not quite ever reaching 0.
Yeah.
So it would be approaching 0, but it wouldn't actually ever hit it again. And so that's how I would go through and figure out what's the derivative from there. I would plot point by point and figure it out, and then go from there. If you were given a different example, like maybe you were asked to figure out which of these functions was f and which of these functions was f prime, what I would do is I would say, okay, from maybe we start with our red function, and we're trying to figure out, is this f? I would go through the same process. I'm like, okay, if red is f, then what would happen is right here, it would need to intersect at 0. Right here, it would need to intersect at 0. Right here, it would need to intersect at 0. And right here, it would need to intersect at 0. So these two look like, okay, yeah, purple is reasonable to be the derivative. But the fact that these don't, that tells us that no, red is not f of x. And so you can kind of do that sort of narrowing down to say, if red is my function, what's its derivative? And you then plot to check if that is matching with it or not.
Okay, yeah, that makes sense. I had something else that just left my brain.
Was it the asymptotes?
Oh yeah, actually, I was just wondering, like, I remember I had to graph something, and I don't remember. I think I might have had a corner hit or something. But anyways, I had an asymptote when I had to draw the derivative.
Mm-hmm.
And like, I don't know how I could tell like when there's an asymptote when I have to draw a derivative of a fraction, if that makes sense.
Mm-hmm. So like maybe you're given some function like 3x over 1 plus x, something like that.
Yeah, this is just graph though, like picture of a graph.
Okay. Well, if we were to graph this from there, the graph as x goes to infinity, we would do a limit. And so that would give us our horizontal asymptote. So if we looked at the limit as x goes to infinity of f of x, we'd find this is equal to 3. So that means that way out here, our function is heading to 3. Mm-hmm. And then if we were to do the limit as x goes to negative infinity of f of x, this also goes to 3. So that means we know that on the other side, it's also going to 3 over there. The next thing is what happens as x goes to anywhere where the denominator is equal to 0. So 1 plus x, as x goes to -1, that's where the denominator is going to be 0. So that tells us that at that point, we either have a hole or a vertical asymptote. Holes occur if the term cancels. Here, 1 plus x does not cancel in the top. Yeah. If we had changed the fraction to be like x minus 2 and then an x minus 2 here, then that tells us we have a hole at x minus 2 because these can cancel inside the limit. And so a hole at x equals 2. If we plug in 2, we get 6 over 3, so that's positive 2. So at 2, we have a hole at 2. So we know we would have a hole right there. So we'd be able to figure that one out. But then to figure out what happens at -1, since it doesn't cancel, we know we have an asymptote. We just have to figure out where is it going on this asymptote. And so this is where we're going to have to do those one-sided limits. So we'd look at what's the limit as x goes to -1 from the positive side of f of x. So this is what happens as x gets close to -1, but x is always bigger than -1. So if x is always bigger than -1, then 1 plus x is going to be positive. So it's going to 0, but it's a positive 0. And then the top, as x gets close to -1, x is always going to be, 3x is always negative. So this is getting close to essentially a -3. So we have -3 over a positive 0. And so what that tells us is negative over a positive 0 is going to be -infinity. So that tells us that on this side, it is heading down towards -infinity. If we were to then do the limit as x goes to -1 from the negative side of f of x, then we still have a -3 on the top, but this time, since x is always smaller than -1, it's going to be going to 0, but is a -0. So -3 over -0 is positive infinity.
So x will always be smaller than -1 because it's coming in from that.
Mm-hmm.
Okay.
Yeah, and so that tells us that our graph is going to just basically connect these different pieces. And so this would be our graph of that function.
Okay, and then 3 would be like considered your horizontal asymptote, correct?
Yep, 3 is a horizontal asymptote.
Okay. I'm trying to make this up. That makes sense. Look at all my stuff that I can think of on the top of my head right now. So, is it an asymptote when it's at corner hit or like differentiable? That makes sense.
So are you asking if like this sort of thing right there?
Yeah.
This is not an asymptote. This is what's called a cusp or a corner. And it's continuous, it's just non-differentiable.
Yeah.
So that is not a discontinuity or an asymptote of any sort.
Okay. And the one I'm talking about is when you're F, because I had they showed me an F of X, and I had to draw the derivative.
Okay, so if like that was our function f of x and we were trying to draw the derivative?
Yeah, but it was a different one. It was like, it was pretty straight. It was kind of like curved out and it almost went like vertically down and then went back out, but it was still considered a function. So yeah, that. And except that vertical line was an asymptote.
Okay. Yeah, so that's because this is, if we were to try and draw the tangent right here, the tangent would be vertical.
Mm-hmm.
So because the tangent is vertical, that's why they're saying it's like a vertical asymptote. Because if you were to look at a graph, so if we were to look at a graph of the derivative of that, the graph is like just below 0 and then gets very, very steep negative. But the problem is because it's a vertical, because it is so steep, it doesn't connect. And so it's going to be something like this. And so we have a vertical asymptote with the derivative as well, because the derivative goes all the way out to negative infinity.
Why is it so close to 0? Is it because because your original function is almost kind of like a...
Yeah, it's almost flat. Like
yeah,
it's down, it's going down slightly, so it's just slightly below 0.
Mm-hmm.
But because it isn't 0, it's not on 0, and so that's why it's going to just be barely below 0.
So if the function was flipped and was slightly going up, it would be above the...
Yeah. Yeah, so if our function was instead like this green function, so let's something like that. Then the derivative of the green function is going to be this blue one. And so that would be just barely above the axis. And then it would go up, have a vertical asymptote there, and then go like that.
Okay. And you know, if it goes to negative infinity because of the asymptote, is that just the way the line is positioned?
Yeah, so in the purple one, because the line is going and then goes down, it's going to be going to negative infinity. On the green one, because it's going and then goes up, it goes to positive infinity.
Okay. Yeah, makes sense. Well, I think that's it for me.
Okay.
And I'll look through my notes see if I find anything else, but I think I got it. Can we just go over just a simple example of trying to find slope by using the definition of f of x minus f of a over x minus a?
What function do you want to do?
Refresh it. Something just simple and easy, just to like, so I can something I can like look at and remember, I guess. And I feel like f of x minus f of a, don't you only use that if you have like points you're going towards? That makes sense.
Mm-hmm. Yeah, that's if you're trying to find, for example, f prime of, oh, that's going to be a not fun number. Let's do f prime of 2. Yeah, so if f of x was 3x squared plus 5x, and then we're trying to find f prime at 2, this is equal to the limit as x goes to 2 of f of x minus f of a all over x minus a. So okay. So if we're trying to find f prime of a, we would need to plug everything in. So let's see. So we get 3x squared plus 5x minus 3a squared minus 5a all over x minus a. Forgot the limit in front. Limit as x goes to a. And so now our goal is to try and get terms to have an x minus a factored out from everything. And the general way to do that with a polynomial is to clump terms that have similar powers. So we're going to clump the x squared and the a squared, and then we're going to clump the 5x and the minus 5a. So this gives us the limit as x goes to a of 3x squared minus 3a squared plus 5x minus 5a all over x minus a. And we are then going to use the very useful property that x to the n minus x to the a is equal to x minus a times x to the n minus 1 plus x to the n minus a to the n, not x to the a. X to the n minus a to the n is x to the n minus 1. Then we have a x to the n minus 2, and there's a long pattern, plus dot 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 plus a to the n minus 1. So we can use that pattern here. So this is going to be equal to the limit as x goes to a of 3 times x squared minus a squared plus 5 times x minus a all over x minus a. So this is equal to the limit as x goes to a of 3 times x minus a times x plus a plus 5 times x minus a all over x minus a. And at this point, because we've factored an x minus a out from everything, we can cancel all the x minus a's. And so this is equal to the limit as x goes to a of 3 times x plus a plus 5 which is equal to 3 times a plus 5, or in other words, 6a plus 5. And so then if we're trying to figure out what's f prime at 2, that's going to be 6 times 2 plus 5, or 17. And this is nice because if you remember your derivative rules, you can find the derivative and know what you should end up with. And then you can check that. And if it worked out, great, you can be a bit more confident. If not, then you're like, uh-oh, messed up somewhere.
Yeah, you just did normal derivative. So yeah. Makes sense. Okay, that's it for me.
Okay. Good. You are welcome. Good luck on your test. I hope you enjoyed this video and that it was helpful for you. Please check out some of my other videos, and please like and subscribe if you have not already so I can continue to make these sorts of videos. Have a great day and good luck with the rest of your math.